This is the video for example 12 about moles and equations. Now the most useful aspect of moles is in determining the required mass or volume of a reactant required to produce a set amount of product, or in determining the mass or volume of product if a certain amount of reactant reacts. So this is where we actually start applying moles to real world sort of situations. And in these sort of problems we solve, you'll be given, in the questions, enough information to determine the number of moles of one species only. And then usually you've got to find the mass or volume or concentration of a second species, and you do that by using the mole equation, or the mole ratio. And the general procedure for solving these problems is, first of all, you write the balanced chemical equation, and you've got to make sure your formula are correct, so please make sure you use your cross method. Get your equation balanced first. If your equation is not balanced and your formula are wrong, you won't be able to solve these problems. The next thing you do is you figure out the mole ratio between the species you know about and the species you're looking for. You find the moles of one species, the species you've been given data about, you find the moles of that species. You use the mole ratio to find the moles of the other species you're trying to find information about, and then you calculate the mass or volume or whatever you're asked to find for the second species. So it's a nice sequence of steps using your knowledge of moles, using knowledge of equations and the mole ratio, and then using your knowledge of mole equations again to find the final answer. Now in the past we've been talking about a method of making sure we answer questions properly, and we called it DISORD. You get your data, you write down your equation, you substitute your numbers, you get your answer, you check your units, and then you double check your significant figures. And that's if you're doing a simple calculation just involving substituting numbers into a formula. This is a bit more complicated though, because we're actually using equations and mole ratios too. So we need something a bit more powerful than just DISORD. We've got to use this instead. This is the demon sword. And in these sort of questions, we get the data, we write down our equations. There's some extra steps here. We find the moles of this first species. We use our mole ratio from the equation to find the ratio between species 1 and species 2. And using that ratio, we find the moles of species 2. Now we've got the moles of species 2. That's like going back to this sort of question again. Now we can substitute that into our equation. We can get our answer, whether it's the mass, or the volume, or whatever else is about that thing we're trying to find. Get our units, and double check significant figures. A little picture, which at first might seem like a scary spider and freak you out a little bit, this actually helps you a lot when solving moles problems. Usually in moles problems questions involving an equation, you're told enough information to find the moles of species 1. You might be told the particles or mass or gas volume or concentration, we'll do this later on, or heat change, which we do in year 12. You'll be told something about one of the chemical species. And from that information you're given, you can find the moles of that chemical species, because we've got a whole range of mole equations we can use to find the moles of that species. So we get to this point here, we've got the moles of species 1. But then we've got to find the moles of a second species, and the way we do that is via the mole ratio in the equation. So we've got to get our equation right, and we can use that mole ratio thing we've been dealing with to find moles in equations, and using that, knowing the moles of species 1, we can now find the moles of species 2. And once we've got the number of moles of species 2, then we can solve the problem, because usually we're asked to find something about species 2, whether it's the number of particles or the mass of species 2, or what volume of gas is produced, or what concentration of solution is produced, or what's the heat change, things we'll do later on. And once we know the moles of species 2, we can calculate those things by using our equations. We've got a whole range of equations that let us calculate that. So usually in these sort of problems, we start with, at one point over here, we find the moles of that species, use the mole ratio to find the moles of the second species, and then we follow whichever path will take us down to the right answer. So to see how we do that, here's an example, example 12. Our scientists at the Galen lime kiln, that was very relevant when I was looking back at Young, needed to produce 1.5 tonnes of lime by heating, decomposing, calcium carbonate. And she needed to determine, well, what mass of calcium carbonate does she need to heat to produce 1.5 tonnes of lime, and what volume of carbon dioxide pollution we produced. And just as a note, lime is just calcium oxide, so we got some data. First step is the data. What do we know? We know that lime is calcium oxide. So what have we been given? We've been told mass of calcium oxide, or mass of calcium carbonate, or the molar volume. Well, we've been told the mass of calcium oxide is 1.5 tonnes. We've got to convert that to grams, because chemists use grams. So 1.5 tonnes is 1,500 kilograms, or converting that kilo into 1,000, because it means 10 to the 3, that's 1,500,000 grams. We don't know the mass of calcium carbonate, that's what we're trying to find, but we do know that the molar volume, based on the second part of the question, is 24.79 litres, based on that temperature and pressure. So we've got some data from the question. The next thing is an equation. Well, what equation are we talking about here? Usually this is a chemical equation when we're using the demon sword model. And the chemical equation, heating up calcium carbonate, you get calcium oxide and carbon dioxide. Just like in class we heated up copper carbonate, and that turned into black copper oxide and carbon dioxide, it's the same thing if you heat up most metal carbonates. So we've got an equation now. The next thing, we want to find, the overall goal of our question is to find the mass of calcium carbonate. And we've got an equation for that. Mass of any chemical is nanomoles times molar mass. And we can easily find the molar mass of calcium carbonate we don't know the number of moles yet. So we need to find the number of moles of calcium carbonate before we can calculate the mass of calcium carbonate. And that's where this mole ratio thing comes in. We can find the moles of calcium oxide because they've given us some data. Then we can use that mole ratio to calculate the number of moles of calcium carbonate, and from that we can calculate the mass of calcium carbonate. So looking at this picture, let's see how that works. We've been given a mass of calcium carbonate. We can convert that mass of calcium carbonate to a number of moles of calcium carbonate. So in this case, we've been given the mass of calcium oxide, We can use that to find the number of moles of calcium oxide. That means we've got the moles of our first species, which is calcium oxide. We want to find the moles of that second species, calcium carbonate. We have an equation, and we can use our mole ratio to convert the moles of calcium oxide to the moles of calcium carbonate. Once we know the moles of calcium carbonate, we can go along this path here, using this equation, to find the mass of calcium carbonate. So let's see. Can we find the moles of calcium oxide? Well, we know the moles equation here is number of moles equals mass over molar mass. So you see we can figure out what we put in here. Well, yes, we know we've got to put the mass in, which is 1.5 million grams, and we can put the molar mass of calcium oxide in, which is 40.08 plus 16. See if you can calculate the answer for that. If you want to pause the video, you're more than welcome. So the answer you get in your calculator will be around 26,747.5 moles. And when we're doing these questions, we're going to use multiple steps, so it's so important you store the whole number in your calculator rather than rounding off or writing down the number on the screen. If you don't know how to store numbers in your calculator, this little tip will help you. Once you've done a calculation and you've got a number on the screen, I always press answer then equals, and that ensures that when you're storing the number, you're storing the actual number itself, you're not storing the pluses and times and equation you typed in. To store that number that's on the screen now, you press Shift, you press the Store button on your calculator, which is usually above the RCL button, so you just press Shift and the RCL button, and then you press A. Now, above one row of your keyboard on your calculator, there'll be a series of red letters. On my calculator, it's above the negative sign in the brackets, above the hype, the sine, the cos, and the tan. All those red letters are different memories in your calculator. So what we're going to do is store this in memory A. So we've got our number here. We've pressed answer equals, we've pressed Shift, Store, A. That number should now be on your calculator as equal to A. So every time you use A, you're using that exact number, not a rounded off number. So the next step, we've got the moles of our first species, we're down to finding the ratio, and that's come straight from our equation. It's easy to see the ratio here between calcium carbonate and calcium oxide is 1 to 1. So number of moles of calcium carbonate on 1 equals number of moles of calcium oxide on 1, or they're just the same number. That's an easier way of saying that. So therefore the number of moles of our species 2, which is our calcium carbonate, is exactly the same as the moles of the calcium oxide, 26,747.5 moles. Now we can do our substitution step. We want to find the mass of calcium carbonate. Mass is number of moles times molar mass. If you want to pause it here and have a go at figuring that out, you're more than welcome. So we put this in here. We put in our moles of calcium carbonate, 26,747.5, but I'll put that in orange because you want to use that number that's stored in your calculator. You want to times that by the molar mass of calcium carbonate, which is this here. But how are we going to get this number out of our calculator? What you do is you press alpha on your keyboard, and then you press that same button A. For example, I'm using memory A, I'll be pressing that minus sign in the brackets because that's my alpha A memory. So you press alpha to tell the computer you want to use your memory, then you press A, and that'll bring that number back. Then you just press times, because you want to times it by this here, so you press times, bracket, 40.08, blah, 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 etc., etc. And that'll mean using that full number, not a rounded off number. And when you do that, you should get 2,677,157.6 grams. Now the reason we've got units in grams is because we're using grams all the way through, and chemists use grams in our calculations. But there's one more thing we've got to think about. We've got to think about significant figures. Now if we look at our data, we were told we've got 1.5 tons of lime, and therefore there should be two significant figures, so that rounds off to 2,700,000 grams of calcium carbonate required, or just 2.7 tons. Second part of the question is, what volume of carbon dioxide pollution is produced? Now we've already done a whole lot of calculations, don't have to do the whole lot over again. We've already done the data and equation, and we know the moles of calcium oxide and the moles of calcium carbonate. So we can look at our equation. Our equation is 1 to 1 to 1, so we can say number of moles of calcium oxide divided by 1 equals number of moles of carbon dioxide divided by 1, or even simpler, those number of moles must be equal to each other. And we already know that number of moles because we've already stored it in our calculator as 26,747.5. So what we're looking for now is the volume. Do we have an equation for volume? Yes, we do. Volume equals number of moles times molar volume. The molar volume for this question is 24.79 litres because we've been given that temperature and pressure. So the volume of carbon dioxide is just that 26,747.5 times by the molar volume. Once again, don't forget to get that number out of your calculator. You press alpha, then A, then your times, then you can put this 24.79 in. You press equals, you should get 663,070.6 litres. Once again, though, we've got to convert it to two significant figures. We do that, we get 660,000 litres of carbon dioxide gas has been produced.